Welcome. This is the third video on histograms, and in this video we're just going to build a relative frequency histogram. And the relative frequency is referring not to the total count of number of people who had a height between two values, or in our case, 4 people scored between 70 and 80. We're going to instead count, well, how many is 4 relative to the whole? So we'll use we will use a measure relative frequency instead of frequency. So counting relative to the whole instead of just raw numbers. And the way to calculate relative frequency is just as if you were calculating proportions. And remember, proportions are the number that you get on the way to calculating a percent. So if there's only 0 is your count, that's still 0%, or the relative frequency is still 0. All of these are 0. And here's our first one where it's a non-zero value, and we're talking about 1 out of 20. And 1 out of 20 is 5%, but also 0.05. The next one is also 0. 2 will be twice as much as 0.05, so 0.10. 4, twice as much as that. And 8, twice as much as that. But just to make sure, like, the calculation we're doing here is 8 divided by 20. And why are we doing 20? 20 is the total number of scores. So you could say 8 out of 20 is 40%, or the relative frequency, if there are 20 total, of 8 is 0.4. 5 is 0.45. Because each count, I'm sorry, no it's not, 0.25. Because 5 is 25% of 20. And so the way to make the histogram that reflects this data is to still put score on the horizontal. So the numerical variable will always go on the horizontal. We're still measuring the scores in clusters of 10. So our bin size is measured at 10. And the only thing that's going to change here is the vertical scale. So we need relative frequency over here. And we need to build a scale that will accommodate 0.4. So if we go up by 0.05s, we can accomplish that. And so we have plenty of room. And then it's the same rules apply. In the previous example, we were using the frequency to measure the height, and now this will be the height of the bars. So relative frequency is now measuring the height. And the first non-zero height we have is in the 40 to 50 range, and the bar measures 0.05. The 50 to 60 bar has a 0 height. The 60 to 70 bar is a 0.10. The 70 to 80 bar is twice as tall as the 60 to 70 bar. And the 80 to 90 bar is twice as tall as that. The 90 to 100 bar raises to 0.25, which is 5 blocks tall on our scale. So there you have it. There's a relative frequency histogram where, again, you should ask yourself, what does 1 bar mean? And we can just do that here. We can say this bar right here. And what does it tell us? This bar says 10%. of the scores were between 60 and 70. So let's move on to some questions. Why would you choose to make a relative frequency histogram instead of a regular frequency histogram? Regular meaning just without the qualifier of relative. So using frequency, you get actual numbers. Whereas relative frequency just gives you proportions. So that's what's happening. Why might you choose one over the other? You might want to emphasize what portion of the population fits a category, fits a bin. Or you might want to emphasize number, how many. So it's just all about emphasis. How many fit a bin. You know, if your numbers are all weird, like your total, if your total added up to like 8,122 total individuals in your sample, it might not be, you might feel like your reader would get bogged down with the specifics. But if you tell them, 30% are between 60 and 70 centimeters tall, or whatever your numerical variable is, that might be easier to interpret. So it's about what you're emphasizing. Emphasize portion, or emphasize how many. And then let's ask one more question about design principles almost. What effect would be had by making the scale go to 1 instead of 0.5? What I mean by this is, the maximum number we had here was 0.5, but we could have maxed out at 1.0. 1.0 is the highest relative frequency you can have, because when you're calculating relative frequency, you're doing a fraction and you're counting how many out of the total number. And so you can never have a fraction that's more than 1 in this situation, because the numerator can never be more than the total. But the question here is about, what if we had instead used a scale of 1 instead of 0.5? And you should think about this for a second, so maybe pause it before I draw a picture, but a 1 at the top here, then each little tick mark would need to go up by 0.1 instead. And then to measure out 0.5, this bar would need to be half as tall. And likewise, measuring out 0.1, which was the height of our bar in purple, it would need to be half as tall. And so what would happen is all of the bars would get half as tall. And so by shrinking the scale, or rather expanding the scale, you would shrink the bars. And so this one would just be half of its current stature. So the answer here is all the bars would decrease to half of their size. All right, see you in the next video.